Welcome to the last video of this lesson, Unit 2, Lesson 4 on Mathematical Induction. We're going to take this section and explore finite differences. So what is a first difference, or what do we mean by a finite difference? You have explored functions in the past where you were given the algebraic representation or the graphical interpretation. And we've always said, when in doubt, t-chart it out. So we're going to look at these t-charts a little bit more in depth. Aren't they really just sequences of numbers? Aha, math. So if we look at x's, the x part of this t-chart is pretty straightforward. They're going up by ones. But let's look at what is happening in the first term of the y sequence versus the second term. So from -2 to 1, we've increased by 3. That is a first difference. From 1 to 4, the second to third terms of the sequence, I've also increased by 3. From 4 to 7, I've increased by 3. Same with 7 to 10. 10 to 13, 13 to 16, 16 to 19, and 19 to 22. The first difference of this sequence of numbers is a constant of 3. You can also think of that as a rate of change. So what functions have a rate of change that is constant? Linear ones do. So this is a linear function, and instead of giving you it in mx plus b form or dn plus c form as an arithmetic sequence, I gave it to you and we looked at the first difference or the finite differences to determine that. Now, if I look at a graphical interpretation, I did not plot every single point because many of the points would go off the graph, but the ones that fit, like -3, -2, -2, 1, -1, 4, 0, 7, and 1, 10, when you look at that scatter plot, you can see that this is a linear function. Let's do another one. Let's look at this t-chart, or this sequence. Okay, again, the x's go up by 1. Now let's look at the y's. The finite difference of the first term to the second term, I added 2. From 5 to 7, I added 2. 7 to 9, I added 2. But when I get to 9 to 7, now I'm subtracting 2. 7 to 5, I'm subtracting 2. 5 to 3, I'm subtracting 2, and so on. So this can't be linear, because if it was a linear function, then my first difference would all be a constant rate of change. I have a constant rate of change of 2 until I hit 3,9, because 3,9 is a turning point. Then my constant rate of change is -2. So what kind of function is this? Well, I know quadratics have a turning point, but we're going to talk about those later. This is an absolute value. If I would plot those points, 0, 3, 1, 5, 2, 7, 3, 9, 4, 7, 5, 5, and so on, then I would get a graph that looks like an absolute value. So absolute values have finite differences where the first difference is the same numerical digit, but at some point the rate of change changes sign. Now we're going to talk about two functions where we're going to have to do a second difference. For those of you in physics, it means we have to talk about acceleration. We have to talk about the difference of the difference. So again, if I look at the sequence of numbers, the x's are going up by 1s. With the y's, my first difference from the first term to the second term, I subtract 640. And again, that wasn't, you can use a calculator to get those differences. From 623 to 303, I subtracted 320. From 303 to 143, I subtracted 160. 143 to 63 is -80. 63 to 23 is -40. 23 to 3, I subtracted 20. I subtracted 10 for the next difference, and my last difference is a difference of 5. So notice that this first difference is not constant. Therefore, it's not linear. I also don't have the same rate of change where part of it is a positive rate of change and part of it is a negative rate of change, so it's not an absolute value. So because I basically have a hot mess for the first difference where they're all different numbers, I have to find the second difference. But you have to determine a common pattern for the second difference. And if you notice, from 80 to 40, that's a difference of adding 40, and from -40 to -20, I'm adding 20. So my second difference is not a pattern of adds and subtracts. It's not arithmetic. The second difference is geometric. I am multiplying by a factor of 1/2. -640 times a half gives me -320. -320 times -1/2 gives me -160. I keep multiplying by -1/2 to get to my next difference. So hopefully you can put this together, that because this second difference is geometric in nature, you actually get an exponential. Now these points don't look the best, and I'm on my laptop, so this is probably going to be one hot mess when I try to trace. But basically what's happening is it's coming down, and then at some point it is going to start to level off at some point. So if the first difference is a bunch of different numbers, and the second difference is a multiplication or division pattern, or it's a geometric series, if the first difference is a geometric series, then you have an exponential function. Last but not least, again, let's look at what this sequence of numbers is doing. Well, 2, 3, 4, 5, 6, 7, 8 in the x column is all going up by 1. And yes, if they're not going up by 1, it's going to affect the rate of change, but we're not going to get too complicated with this particular section. From 60 to 32, I subtract 28. The next difference from 32 to 12 is I subtract 20. From 12 to 0, I subtract 12. Then I subtract 4. But then I add 4. Something's going on there. 0 to 12 is 12. 12 to 32 is 20. And 32 to 60 is 28. So again, this cannot be linear because the first difference is not constant. It cannot be absolute value because I don't have the same number as my rate of change where it just switches from a positive to a negative rate of change or vice versa. So I do have to look at the second difference. Well, is this first difference geometric or arithmetic? This first difference is arithmetic. It has a difference of plus 8 every time. I have a common difference between those values. So when the second difference is a constant, or when the first difference is arithmetic, we have a quadratic. And again, I didn't graph all of the points. I graphed the points that would look nice between 10, 10, 10, and 10. So I graphed the points 4, 12, 5, 0, 6, negative 4, 7, 0, and 8, 12. And you can see by the points that we get a parabola. So for example 6, we're going to write the first 5 terms of the sequence beginning with the given term, and we're going to calculate the first and second differences of the sequence. Does the sequence have a linear model? Ooh, I misspelled that, so pardon me on that. So does it have a linear model, a quadratic model, or neither? All right, so let's get the first 5 terms first. A sub 1 is 0, and then they give me a recursive pattern. So here's the work for that. A sub 1 is 0, and that's given. When you want to find the next term, a sub 2, and I input 2 into the formula, it basically requires me to find a sub 1, which is 0, add 4 to it, and I get 4. When I want to find a sub 3, that requires me to find a of 3 minus 1. So basically 3 minus 1 is 2. I have to use 4 from the previous term, add 6 to it to get 10. When I want to find the fourth term, I have to take the third term and add it to 2 times 4 to get 18. And lastly, for the fifth term, I have to use the fourth term of 18 and add 10 to it to get 28. So now let's put those values in a t-chart. Okay, 1, 2, 3, 4, and 5. So that represents the first term, the second term, the third term, the fourth term, and the fifth term. And I got the outputs of 0, 4, 10, 18, and 28. So from 0 to 4, I get 4. From 4 to 10, I get 6. From 10 to 18, I get 8. From 18 to 28, I get 10. So I can rule out that it's linear, because if it was linear, the first difference would be constant. I have to find a second difference. You have to determine if 4, 6, 8, and 10, is that arithmetic or geometric? Well, from 4 to 6 is 2, 6 to 8 is 2, 8 to 10 is 2. So I have an arithmetic sequence because it is a common difference. Therefore, when my second difference is arithmetic, this is indeed a quadratic. So without having something in ax squared plus bx plus c form, this formula, this recursive formula, is a quadratic in nature. And for our last example, we're going to find a quadratic model for the sequence with the indicated terms. I'm told that the initial term of a sub 0 is 7, that a sub 1 is 6, and a sub 3 is 10. And if we know that the general form or standard form of a quadratic is an squared plus bn plus c, and instead of using x's, I'm using n's because we're talking about series and sequences, I can figure out some information. If I know that a sub 0 equals 7 and I plug it in, A sub 0 is equal to a times 0 squared plus b times 0 plus c. So a sub 0 is c, and I know that that is equal to 7, so my constant of this quadratic is 7. Now I can use the a sub 1 equals 6 and do the same process. Substitute in 1 for n. A sub 1 is then equal to a plus b plus c. And I know that 6, which is a sub 1 by substitution, is a plus b plus c. Hold on a minute and I'll tell you what we do with that shortly. Last but not least, I'm going to deal with a sub 3 equals 10, that the third term is equal to 10. So I can input, since my n is 3, I have a times 3 squared plus b times 3 plus c, which gives me 9a plus 3b plus c. And if I substitute in the value of 10 for a sub 3, I get 10 equals 9a plus 3b plus c. What we have, friends, is a system of equations. How do I start? Well, I'm going to write my 7 equals c, 6 equals a plus b plus c, and 10 equals 9a plus 3b plus c as a system of equations. Now, I know that c is 7, so this is going to make my system of equations a little bit easier. When I go to the next step, I've substituted in 7 for c, so I get a plus b plus 7 equals 6, 9a plus 3b plus 7 equals 10. When I subtract 7 from both sides on both of those equations, I get a plus b equals negative 1, and 9a plus 3b equals 3. This is now a simple system of two equations, two unknowns. I'm going to choose to use the elimination method. So I multiplied a plus b equals negative 1 by negative 3. So that yields negative 3a minus 3b equals 3. And when I add that to 9a plus 3b equals 3, I get the b's to cancel. So I'm left with 6a equals 6. And when I divide both sides by 6, a is 1. Then I go back and I know that a plus b is equal to negative 1. And so I substitute in 1 for a. And I get that b is negative 2. So when I put this all together, where a is 1, b is negative 2, and c equals 7, and I put that into the general form of a quadratic, my final general formula of a sub n is equal to n squared minus 2n plus 7 when I have a quadratic model with the given information. 591 for more examples, and your last learning opportunity for this section is page 593, numbers 37 to 49 odd. Good luck!